Hi everyone, welcome to Python tutorials where we are focusing a bit more on image processing related tasks. In the last couple of tutorials, we looked at a couple different types of machine learning or deep learning categories. The one in the last video, we looked at binary classification, and the one before that, we looked at regression. So let's continue this path and let's extend our binary classification to multi-class classification. Okay, and just to give you a quick reminder about what multi-class actually means. Multi-class is we are classifying an image into one of many classes that is available. Again, the key term here is one of many classes. So it can only become a part or be classified as one class. That's it. Multi-class refers to the fact that there are multiple classes that are available. So for example, this image can be a nucleus or a mitochondria or ribosomes or one of these others. But the classification tells us that this is 3.4% nucleus, this is 91% mitochondria, and so on. So at the end of everything, we classify this as mitochondria. That's it. All of these other classes are the available classes. Maybe the next example makes this a bit more intuitive. So there is a dataset called CFAR10. This is exactly what we are going to work with in today's tutorial. And this dataset is an excellent dataset to practice multi-class classification in general, because these are all relatable things. So there are a bunch of images, in fact 60,000 images, each very tiny image, 32 pixels by 32 pixels. So the training is usually fast enough. And they're divided into 10 classes. That's why this is CFAR10. What are these 10 classes? Here they are: airplane, automobile, bird, cat, and so on. And as you can see that, you can see the images right here. And you can directly download this using Keras, meaning you don't have to separately download and handle and all that. In fact, they are separated into training and testing data. All you need to do is just write these two lines of code. From keras.datasets, import CFAR10. And then just write these lines, because when you load the data, it's going to load it as xtrain, ytrain, xtest, ytest. So you don't have to split it any further. Okay, so let's with this knowledge, let's jump into our Google Colab and continue this training. Okay, again, as usual, I'll share the link to this file. So you don't have to bother writing it down right now. So just focus in understanding what the video is about, what this tutorial is about. So we are trying to learn about multi-class classification. So we have a bunch of images, and the goal here is to write Python code using Keras to compile a model, to actually train a model that can classify images into one of these 10 categories if we supply it an image. So I give it an image of frog. Hopefully it will tell me with certain confidence that it is an image of frog. So it is restricted to only these classes. If you supply an image of something that's not here, like a helicopter or something, then it's going to classify it as one of these. That's it, right? So this is what classification is typically. You have a handful of these, and then it belongs to one of these classes. That's it. Okay, so this data set has 60,000 images, like I already mentioned. So let's go ahead and import the right libraries down here. So as usual, matplotlib and numpy for sure for plotting and handling our arrays. And then from keras.models, we are using sequential method to put our model together. And I always import image data generator, just because you never know when you would be using data augmentation. So I imported this just in case if I would like to use data augmentation. Again, the other things that are pretty common: batch normalization while you're putting your model together, convolution layers, max pooling layer, dense layers, and flatten before dense, right? So this is required for you to, we are dealing with images, so we need conv layers. And from keras.datasets, I'm going to import CFAR10. This is how we are going to get our hands onto this dataset. And also from keras.utilities, let's import normalize in case you want to normalize the images, or you can divide the image pixel values by 255 to scale them. And I'm also importing toCategorical. Again, this please watch my video on this categorical or one-hot encoding. This is multi-class classification, meaning our input data needs to into our neural network needs to be converted to one-hot encoding, because we'll be using cross entropy as a metric. So we'll get there in a minute. Sorry, not as a metric, but as a loss function. And from the layers, I'm using dropout. Again, I forgot to include it here, so I added it down here. And optimizers, I'm importing stochastic gradient descent and RMS prop. So you can experiment with either of these. Okay, so let's go ahead and run these lines. Oh, I should have connected to a runtime. Let me quickly make sure I'm using GPU. Yes, that's required. Okay, now let's unpack our data set. So cfar10.load data. So let's get X-train, Y-train, and it's going to, if it's the first time, it's going to download it. You can directly download it from here if you want, okay, from this link. So we have 50,000 images as part of training dataset. We have 10,000 images as part of testing dataset, and each image is 32 by 32 by 3. And my Y values, which is our Y train, right? Training labels. You have 50,000 labels corresponding to these and 10,000 labels corresponding to these. So far, so good. Let's view a few images, like for the first few images, first 9 images, plotting into 3 by 3 grid. And there you go. That looks like a frog, a horse, a bird, probably automobile, and so on, a boat. Okay, so you can print corresponding labels if you want along with this, but I'm just looking at some of these images. Okay. We need to normalize the pixel values or scale the pixel values. So I like to divide these just by 255. That because there is no other attributes other than just the pixel values. So dividing these by 255 works fine. Okay, so let's do that for training and testing. And let's print a few training values right now, okay, to see before and after categorical. So if you look at your Y train, right, this is our training. The label for the first image is a label of 6. What is 6? I don't know. If we go back up, 6 is frog. Okay, that's the label of 0th image. I guess it's referring to this image. Okay, what's the next image? The label is 9. What is label 9? Let's go back and look at the label 9, which is a truck. So I guess it's referring to this one, the next one. Okay, and then I'm printing a of 10. I don't have an image there, but the label is whatever the 4 is. The label here is a deer. I hope so far so good. The reason I'm printing this is to show you how the result looks like after converting to categorical. And how do we convert that? Again, we imported this method, right? So you just apply that to your Y train. And I'm assigning that to a variable, new variable called ytrain categorical. So now let's go ahead and print for the exact same ones. Okay, how does the output look like? So there you go. This is what categorical is. I don't think I can explain any better than showing you the output. So in this case, the first one is 6. So let's look here. So 0, 1, 2, 3, 4, 5, 6, right? The 6th one has a value of 1. That means the label here is 6. The label here is 9. Yeah, the label here is 4. So basically, to categorical means everything else is 0 except for the one that actually belongs to that specific class. That's why this is called one hot encoding, because there is only one hot value. Everything else is 0. Okay, next, let's put our model together. Again, how do I know this one works well? I don't. I experiment with something, or I copy from somewhere else, right? I mean, you have to experiment and build, engineer something, not completely random. This is based on my educated guess. So I want 4 or 5 convolution layers. Okay, and in the binary example, the last time I used only, I think, 3 convolution layers. It didn't work very well. I did some experimentation after the fact, and adding another convolution layer really helped a bit. So let's go ahead and start with 1, 2, 3, 4, 5, 6 convolution layers, and then a dense layer. And also this time, let's include dropout, because this is a very deep, like 6 convolution layers. I don't want this model to be overfitting. So I am adding dropouts in between right here. Okay, this helps with generalizing the model, or minimize the overfitting problem. So I start the first one with 32 filters. Again, this is pretty straightforward. 3 by 3 kernels, 3 by 3 kernels. This is the same, and ReLU activation function for any of the hidden layers like usual. And kernel initializer he uniform works very well with convolution layers. So I'm going to use he uniform or he normal, either way. And padding equals to same means the output from here is going to be the same as my my input, so I mean the image wise, so I'm not losing the image dimensions as a function of convolution operation. I will do that as a function of max pooling if I'm doing max pooling. Okay, so this is my first layer. The next one is very similar right there, and for this one we are doing max pooling, which means the size of the image changes after max pooling. Like if it's 2 by 2, the size of the image goes by half, and I'm dropping 20%. And then 64 convolution, batch normalization. I think I included batch normalization after every convolution there. This is a result of a bunch of experimentation, by the way. And there you go. And before going into the dense layer, again, please remember you have to flatten this 2D, because dense layers do not work in 2D, they work in 1D neurons, right? So that's what you have to do right there. And activation, I'm still using ReLU because this is a hidden layer, not the output layer. So pretty much the same right there. And comes the final output layer. And in the output layer, my dense 10. Why 10? Because I want the output to be 10 values, a vector of 10 values. And these are all probabilities because we are using an activation of softmax. And all these probabilities add to 1 because this is softmax. That's how softmax works. So the output is going to be 10. And each of this is a probability representing the probability for that image to be part of that specific class. So if the first one, I get a probability of 0.6 and rest of them add to 0.4, then I know this image is classified as this first probability because that's the highest. Okay, so that's how this works. And let's compile it using stochastic gradient descent as our optimizer with a learning rate of 0.001 and momentum 0.9. We talked about all of these in the past. So hopefully things start to make sense to you now that you're educated on activations and dense layers, what are stochastic, what is optimizer, and so on. And for the last, we are going to use categorical cross entropy. Okay, this is why you need to convert your images into categorical, right? I mean your labels, sorry, into categorical. There is another loss that is similar to categorical cross entropy called sparse, I believe, cross entropy. For those, you don't have to convert them into categorical, but frankly, I haven't used that much. I never found the need to do that. Categorical cross entropy works very well for multi-class classification. And the metrics we are going to track are accuracy. Now, one thing I need to mention is this accuracy is the accuracy of us getting an image correctly classified. Okay, I think I'll make another video, the next video, where I talk about top 5 accuracy, meaning I'm okay if this image is classified into the top 5 classes. Okay, so we'll talk about that. Let's not focus for now. And this is our model, and let's go ahead and print the summary. I hope we ran all the other ones. Yeah, lines. So it's going to print out our model. There you go. So finally, you should see 10 because we want 10 values as output. And you can add callbacks. Again, I commented out some of these callbacks. The only one that I left is the early stopping, because we would like to stop this when it reached the minimum in terms of the loss and in terms of validation loss, and with a patience of 10. That means, okay, even if you find a minimum, just go 10 epochs further to make sure that this is indeed the minimum. Okay, so that's what this is. And let's go ahead and define our callbacks. Again, I'm not spending too much time describing these. We already talked about these in the past. So let's go ahead and fit the model. Let's run for 25 epochs and see how the result looks like. Okay, so here we are providing X-train and Y-train categorical, right? So we have to provide categorical as input. Same thing with X-test and Y-test categorical. And our callbacks are given as callbacks list right here. Okay, so it will start any second now, and I'll gauge, let's see how fast or slow the training happens. If it is slow, I'll of course pause the video so you don't waste your time staring at the screen while it's training. But let's wait a few seconds for it to get started. And I noticed that Google Colab is a bit for whatever reason, slightly slower today compared to my normal use. But let's see. Here it took about 40 seconds for the first one. I think the second one makes more sense. Okay, it's taking 8 seconds, so 25 should be done pretty quickly. But while this is running, a couple of things I would like to mention. Again, we have 50,000 images, correct? And we are taking a batch size of 64. That means it takes apparently 782 iterations to see all the 50,000 images as part of training. So the training is happening after each epoch. It sees all of your 50,000 images, but at a time it's modifying weights after seeing 64 images, and then loads the next 64 and next 64 until it sees all of those, and it takes 782 iterations to get to that point. Okay, that's what this means. And if you look at the accuracy, it's improving. Hopefully it improves a bit further. So we'll see after 25 epochs. So let me go ahead and pause the video and continue this so we don't stare at the model training. Okay, so this is done, and a couple of things I would like to mention here is, if you look at the accuracy right there, somewhere in the middle, right, 0.6575, which is the training accuracy, and the validation accuracy 0.67. You see how it went up to like 70 and then 70, right, and 72 and then 72. I'm showing this as a good sign because my validation and training are going up or down accordingly. That means I have a very good model, like training in a nice way with not much overfitting. We'll see that when we plot our training curves, but looks like the maximum accuracy we went up to is about 73%, which is not bad for a problem where we have 10 different classes. Just imagine you have an image that can be classified into 10 different classes, and you're actually getting 73% accuracy right there. Now the question is, if I get it wrong, is my class in the top 3 or top 5? That's what we'll see for the next video. Okay, but for now, let's see, evaluate the model. Again, when we evaluate this, it's going to print out, or it's going to return the loss and accuracy, because that's the only metric we follow. In the next video, let's go ahead and add top 5 accuracy so we can look at that value. Okay, 73.2, we already know that, right? So that's the validation accuracy that we are getting. Now let's go ahead and plot the training curves so we can infer something about this. Yeah, I think given maybe 10 or 15 more epochs, we would have gotten slightly better. You see how this is heading up there, maybe 75 to 80%, but I will be surprised if we get anything above 80% with this specific model. Now let's go ahead and plot. So all I'm doing here is I'm just taking my model and predicting on a test image. And that test image has to be pre-processed exactly the way we process our training images, right? So that's all this part. And then I'm plotting them, and instead of printing the output as 0 or class 2 or class 3 or class 4, I'm just assigning each class, the corresponding label, and I'm printing that label. So that's all this part of the code does. So let's go ahead and look at this. So we can't even tell. If you squint your eyes, maybe that looks like a cat, but this did a great job in predicting a cat as a cat. This, well, the original class is horse. We are calling it a deer. I think it can be a deer if you look at it. So wherever it's making a mistake, it seems to be logical. Let's actually see a few more. This is an automobile, correct class. Airplane, correct class. Yeah, I can tell if that's a cat or a dog with that image. Sorry. Truck, and it called it an automobile. I mean, a truck is an automobile, right? But deer, oh, this is where it got it wrong, right? So I like these type of examples where I'm like, why does it think this is a ship? But anyway, this is a great example where it got it blatantly wrong. Okay, so this is multi-class classification for you. Again, this is very similar to binary class classification, except there are I think only one thing or a couple of things that you need to pay close attention to. One, converting your labels into categorical labels. That's one step, and the next thing is Next thing is when you define your model, make sure the output, the dense layer, has the same number of neurons as your predictions, as the number of classes that you're trying to predict. That's the only thing you need to take care of. Otherwise, it's very similar to binary classification. And in fact, you'll see that most of this machine learning is very similar once you get your data into specific order. So like I promised, I'll record another video on top 5 accuracy. Let's call it top 5. It can be top 3. Doesn't matter. Let's call it top 5 accuracy on exactly the same example, so you can easily relate to that. Okay, so let's meet in the next video, and until then, please subscribe to this channel and like these videos, and let's meet again in the next tutorial.